next up, again talking about fire, and we have got all the relative safety components actually. You should be very happy to know that we've turned off all the smoke detectors and heat alarms in here, so if the fire does go up, then yeah. Right, anyway, next up I'd like to welcome Andre, who's talking about special relativity. So, warm round of applause for Lindsay.
What is time? Well, actually, does time depend on who you are? Is time the same for everybody? Well, according to our best knowledge, based on relativity and many, many experiments, the speed of light is constant. It limits how fast anything can move. Apart from a few magical neutrinos, maybe, but that's another story. Now, this is very surprising, because it means that if I were moving very, very fast, say at about half the speed of light, so 150,000 kilometers per second, and I shine a flashlight in the direction of my motion, then unsurprisingly, I would see the speed of the light moving away from me at the speed of light, 300,000 kilometers per second. But the very surprising thing is that you guys would see it moving at exactly the same speed away from you, also 300,000 kilometers per second. Now this is remarkable because it means that the addition of velocity as we're used to it no longer holds. The speed of the light relative to you is no longer the sum of my speed relative to you and the speed of the light relative to me. Now, what does this imply for the passage of time? Say we have a very simple clock. Let's imagine this now. So this clock is made up of mirrors, as you're used to, 2 mirrors, and a particle of light bouncing from one mirror to the other, ticking whenever it hits the mirror. So tick, tock, tick, tock, etc. So if d is the distance between the 2 mirrors, then the time between the ticks, t, is simply d divided by c, where c is the speed of light, which is a constant. Now to make it a bit more interesting, let's illustrate this with fire, of course. Okay. So you're going to have to use your imagination here. Imagine that this is on fire. Okay, let's try again.
On our Joe's actually
we can imagine, and then we'll try later. So for now, we'll have to imagine that this here is a particle of light. So bouncing up and down, and it ticks whenever it hits the mirrors. Tick, tock, tick, tock. Now let's take a clock of exactly the same design, moving very, very fast relative to the first clock. So tick, tock, tick, tock, tick, tock. All kinds of things doing it. Now let's see what happens here. So for the first clock, the distance that the light has to go through to get from one mirror to the next is just d, as we saw. But for the moving clock, the distance that the light has to go through to get from one mirror to the next is larger than d. And since, as we saw, the time between ticks is d divided by c, the distance divided by speed of light, which is constant, the time between ticks is larger. Therefore, for the moving clock, time seems to slow down. The ticks are slower. Now, you may just think that this is a very bad clock. But in fact, if you think about it very hard, you can see that every time measuring device, every clock works on the same kind of principle. I'll try and give you a bit of a hand-waving explanation of this. Again, of course, we have to use fire. Okay, so imagine this is a clock here. So it's a bit of a curious clock, but you know, it's kind of a more complex version of the same principle. So it kind of ticks after some repetition. You need to recalibrate the clock. It ticks after some repetition of a period, and take the same clock moving very, very fast relative to the first clock. The ticks will seem to slow down exactly the same way. The same argument will apply. In fact, if you have a perfect Swiss watch or something, just looking at your watch as you move, you can apply the same kind of argument. So, in conclusion, time is not the same for everybody. In fact, all you need to do is start moving, and the rate at which time goes by changes. And this is why clocks can't work. So if my clock seems to go by in a flash, I hope that's because you found it very interesting, not because I was moving incredibly fast. Thank you very much.
Thank you. Again, I saw my job flash before my eyes there. Now, next up, we have Jake, who's going to talk about quantum levitation. Now, Jake's actually using some liquid nitrogen here that's been cooled down where it's colder than minus 196 degrees. So, yeah, you might need to move. If anything goes wrong, it'll be all right. And anyway, I'd like to welcome James talking about quantum levitation. Big, well, not warm, round of applause.
Thanks. As Simon said, I'm going to be talking to you about quantum levitation. Now, to do that, I'm going to have to explain a bit about resistance and superconductivity. Now, the idea of electrical resistance is probably quite familiar to you. You've got an electron moving through a wire, and it feels the friction and loses energy. But that's not always the case. Now, what I have here, which you probably can't see, is a lump of superconductor. When I cool it down with some liquid nitrogen, get the feet out of the way, it becomes superconducting and undergoes a phase transition, which basically means its electrical resistance goes to zero. Now, you should be able to see on the camera this little trap which I painstakingly built out of really strong magnets. And actually this metal thing wasn't part of the demo, but I was playing with them and can't get them out. So now it should be superconducting. So take out liquid nitrogen, drop it on the magnet, and hopefully you can see that it is levitating a small amount above the magnet. You see it drop down pretty quickly because it heats up again and undergoes another phase transition and gets resistance, so it no longer can levitate. But it's levitating because the electrons have no impedance, so they can move around freely in the material. And that means it can sort of act as a mirror to the magnetic field of the trap and reflect back the magnetic field, keeping it in place. So if you didn't see that properly, I'll be playing with this outside later. So come and make sure there are no strings. So, thanks.
Are you okay? Fine. I'm telling you to my dad and my mum. Right, anyway, hopefully, well, I think we've got away with it. And once if we're indoors, it's no longer my responsibility. Brilliant. Right, okay, so I don't got away with it.